You got it?
It's move a little bit further away.
Okay, yeah. All right. Okay. You have it?
Like we have your voice.
All right, good.
Not my voice.
Let me put it away. Okay.
We are broadcasting. You're welcome.
So we are online.
Drawn by the
Okay.
power. Okay, I can put one up there if you care to have it. You have to worry about getting people's attention.
All right. All right. Okay. Okay. Everybody ready?
Mic on.
All right. Hello. This is Ping, and we are at the Silicon Valley fourth interest group, the April meeting. Okay. Okay. This morning, the topic is basically pre-run of the CPU design workshop that we will do next month. So I just do a little preview and some miscellaneous topics that I can entertain you for this morning. Okay, so this is what I'll do this morning. The first thing is to review or do some demonstration on the Diamond IDE system. And this is the integrated development environment for the Lattice Bravia 2 board, which I have one here. Okay, so this is the kit we'll be using for the CPU design. And the Diamond IDE would give you all the support that you need to do your design and run the design on the Lattice FPGA chip. And I want to also talk a little bit about 8086 eForce version 2.03. You know, the 8086 eForce 1.1 was the original eForce model that we released in 1990. So in the workshop, we'll use the 8080 implementation, the 8080 chip implementation as an example. And on that 8080 chip, I'll be running eForce as you know, test bed. Okay, so you do a chip. How do you know that you got the chip done right? You need to run lots of instructions through it, and so what I did was use the eForce model and change it to 8080 instruction set, and then build an eForce system of that instruction set. And so I tried to use the 8086 eForce as the basis. But the 1.1, eForce 1.1 is really too complicated. So I trimmed down the eForce system for the 8080 implementation. And then I thought that it's probably a good idea to move all the modifications back into the original 8080 eForce model. And that's what I call 2.03. It's a much simpler system. And I hope that that will be the basis for all the other chip designs that if you want to do a new chip. And then if you change the E4 system so that it will run on your own chip, and that will give you a very good test bed to try out your hardware implementation. So here I would this morning I would review many of the historic CPU architectures. Just to, I would like to people, if you want to participate in this workshop, you would pick your favorite CPU and try to implement it on the FPGA. So here are a review of some historical CPU architecture and some mini computers, old, very nice mini computer architectures, and the RISC. And I would skip all the modern microcontrollers, and assuming that you all know and know how to use them, and you know how to program them. Okay, so that's and the last thing I show it on the program, but I didn't get it on the my view for is I want to talk a little bit about the Visual Basic, and this is basically my goal is to be able to program this thing, the Amazon file, and it is only $50. Okay, so if it get a nice screen, very nice camera, nice nice audio, and the internet connection, the whole bit for $50. Very nice screen. Okay, and so if I can program this guy and make my own applications, we can move lots of applications onto this thing. And for one thing, we're talking about with Masa about the music applications, and so lots of things we can move on this platform. And I try to find some platform to program this thing. I still haven't get anywhere, but I think Visual Studio from Microsoft is probably a good platform that allow me to program things and ported the application onto this device. So I'll talk a little bit about that. Okay, so let's get on to the VHDL, or the chip design thing. So what I want to demonstrate, what I want to show you is several steps. The first thing is that you to do a CPU, what you need, the first thing is to write the CPU out in VHDL. And then once you have the all the logic in VHDL, then you need to do the synthesis. The Diamond IDE has all the synthesis tools there to help you. And in the 8080, or I call EP8080 project, I have basically 5 VHDL files. And the EP chip file is the top level design. And in this top level design, you implement 4 devices, and the CPU itself, EP80, and the UART, and the GPIO, 2 IO devices, and the memory. So these are the 4 components that you need physically write down all the specifications, all the logic in these files. And if you assemble or the synthesis tool will be able to synthesize the whole design, and including all these 5 files. So I've if you want to participate in this project, I'll send you all these files. so you can actually do the synthesis on a piece of. Actually, you don't have to have the Bravia 2 board to do this part, because IDE has all the tools which can handle all the logic. So you can do the synthesis and do the simulation all without the hardware, just the Diamond IDE. And once the IDE do the synthesis, you can pick the target. If you want just to do simulation, you can select the simulation option, and it will synthesize the whole thing and provide a target image that you can use the simulator to run on the IDE system. And if you want to program the FPGA, then you need to synthesize in a different option so that you produce an image file which is suitable for downloading to the FPGA to the board. And once you have the board loaded, and then you need a hyperterminal interface, serial I/O, because in the FPGA, in any of the CPU design, you need to add an UART device so that you can communicate, so that the design can communicate with you through the hyperterminal interface. You can use any of the available serial port interface, because hyperterminal is not available now after Windows 8. And the other thing about this, yes, you do the CPU design, you get it synthesized, you got everything done, but you still need to run something in the CPU, and that's what I provided the eForce for. So if you do your own chip, I hope you can find a fourth or something, some program that you can run on it. But if you don't have any force running on your particular CPU, you can take the eForce model and modify it so that it can produce assembled binary file that can run on your target. I'll show you a little bit about how I use the Imagine the Microsoft assembler to assemble the 8080 eForce system, and you can take that as an example, or as example to do your own system if you so desire. Okay, so I also want to show you a little bit about the eForce 203. And as a matter of fact, why don't I do it right now? Because the Mazen assembles the eForce 8086 eForce. Let me see. I think it is the next. Let's go to here. So 8086 eForce can still be assembled with the Mazen on newer Windows platforms, but newer Windows platforms cannot execute the 8086 code. Okay, so but I have an old XP computer, and that computer can still do the assembly and actually execute the 8086 code. So I was able to upgrade 8086 1.01 to 2.03 on this computer, and actually verify that they still work. So let me move on to here. and show you the assembly process. Okay, so I have already loaded up the, but let me go do the buy. Okay, this one goes away. So do the assembly and actual testing. I have this batch file, which does assembly and then the link and do the linking and produce a .exe file. And this .exe file can be executed in the command prompt screen if you order it so. So here I have everything in this file in this folder, and this is the batch file. And if I just call out the batch file, and it calls a CMD window, and it reports the assembler reports it's running okay, and the linker also reports that the link's okay. So we got the .exe file, and then I just push this thing, and okay, and it is actually running. So this is the process that you need to go through and get an image, get a binary image that you can eventually load it on to the FPGA and actually exercise the target system you will build. Okay, this is the assembly source code of the 8086 E4, and I've moved it up to 2.03 because I found that I was very happy to find a copy in my computer 2.02 because I knew that 1.01 is too old, too big, not that good, and in all my later implementation of E4 on various microcontrollers, I have modified the system and eliminated much of the features that I didn't need. So the 2.02, you know, the original E4 system, Bill Minch was very ambitious in that project, and he built a full system basically for multitasking purposes. So it can support many tasks in the same fourth environment. But in all my work over 20 or 30 years, I've never used the multitasking feature except once. And that was when I built a system which has many instruments working simultaneously. And I need the full system which can talk back and forth among these systems. And that's the only time that I need the multitasking. So I eliminate all the multitasking and the catch and throw mechanism for error handling and many of other things. So this thing, another thing is the dictionary. In the original E4 model, we have separated head dictionary, name dictionary, and the code dictionary. And the purpose was that you can, if you do a embedded application, you can throw away the name dictionary. You only keep the code. But I found that keeping the names inside the dictionary is advantageous. In that, for one thing, you can do disassembly with when you have all the names there. Okay, So that was very nice, even in your application, because you deliver a product to the field, and there's always chances that there are errors in field. You get bug reports, so you have to go down to the machine and try to debug it. And there, when you have a full system with full dictionary, it's very advantageous. You can immediately see what's happening and then debug and actually fix the system on site. So here I have combined all the name dictionary and the code dictionary together, and it actually deleting all the features that I really don't need. Reduce the system to about less than 6K. And so I think this system 2.03 is the thing that I will leave for posterity. Okay. And here this morning, I particularly wanted to call your attention to the do use and the user variable implementation. Let me see. Okay, let me switch over here because I have all the things I want to talk here. So in the user variables and and variables and constants in the original E4 systems, these are implemented in high level. Okay, so code word we use the direct thread method, direct thread model. So the code word just contains machine instructions. You execute a code word, you just jump to the head of it, and then you start executing. To execute a colon definition, basically you put a call do list at the head of the code field, and then it's followed by a token list, which are just addresses. So and this way we can implement all the high-level words in tokens. And for user variables, it is similar to call to high-level word to colon word. In that the first instruction is call to user. Okay, so you call to user and followed by an offset. So when it's executing this do user, it would retrieve the address of the offset on the top of stack and fetch it and add to it the UP, the user area pointer. And that gives you the address of that particular user variable. Okay. So if you just want to call the ordinary variable, you call do var, and followed by the value of that variable. And the do var is actually rfetch. So it retrieves the address of this value, and you can store or read. You can read it or you can write it. Okay. So these user variables and the variable were implemented in high level. And I was when using this type of system, especially when you are trying to debug it and single step the machine code. And this, when you hit that user variable, there's a long piece of there are many cycles you have to execute to get to that address. Particularly this plus. Okay, the plus is I don't have a plus in primitive as a code word. Plus is a high level word. It's actually doing UM plus. It adds two single integer together to form a double integer. And then it delete the upper part of it. That's the carry, okay? So this plus involves many cycles. So when I was trying to single step through the code, when I hit that user variable, you just have to hit so many keys to get to the end of it, and I feel kind of guilty in providing it in the for system. So what I doing much more thinking and some experiments, I found out that, oh boy, if I do the user variable in code, what I was left is just the user variable is call fetch. Because when you jump into here to execute a user variable and you do a call, this address is left on hardware stack, which is right there. So it's there already. And if you call the do user, and do user have to push this thing on the return stack, and then you retrieve it from the return stack. Use R from and all these things. So all these things are not necessary. You just call fetch because the address is already there, and use a variable. In the new design, I don't use user area because I don't have because it's not a multi-user system. So I only need one copy of all the user variables. So all these user variables can be specified by an absolute address.
Sorry, is that comma? Is that part of the code you're calling, or is that just something in the text?
Let me see.
After fetch.
Okay. This is just not in the code. Okay. Sorry. And so you just call fetch, and you just fetch the value of it, and the variable you don't even what you need is that address. So it's already there. And all you have to do is call next step to go back to the original token list. And this is exactly what you would implement the constant. The user variable, I define them basically as constants. So this changes the greatly simplifies the user variable mechanism. And I think that if you are going to implement E4 system for your target machine, this is the way to go. Any comments? Good. Okay. Thank you. Okay, I got this one done. Okay, now let me go to the IDE. This is the Diamond IDE. So here, I'm running the project, and the name of the project is EP8080X. And in this project, so here are all the files, all the VHDL files, the 5 VHDL files that you need to do the whole design. And you actually, I have to actually pick this one as the top level module. Okay, you have to specify what is the top level module, and you because here in the same design you probably can pick many different top level designs. For one thing, if you have a test bed, if you write a test bed for your CPU, including all the instructions that you want to execute, and the test bed can be put in here. And when you pick the test bed, it will synthesize with the test bed, so that you can, when you execute it, you can actually see something happening. If you just have this thing, it will, what you will do is go to the memory 0 and start executing. Okay, so you have to put your eForce or your operating system or your test code and include them into the memory specification. This way, the whole thing would come alive and start executing if you turn the power on. Okay, one thing. It's not I think this LPF file. This LPF file is very important if you when you have when you want to test things on the FPGA kit. If you just want to do simulation, it doesn't matter, okay? Because this file allocate signals to physical pins on the FPGA chip. So if you wanted to run correctly, interface to the LEDs, to the switches, and to the UART, this file has to be there, and this file has to be correct. Otherwise, it would not nothing would work. So this is very important if you are actually testing the CPU design on the Bravia board. Okay, once you have all this files there, so what do you do next? The next thing you want to do is to do simulation. And to do simulation, you go to here, the export files. This is the process panel. And then there you can select VHDL simulation file or JEDEC file. And for JEDEC file, that's the image which will be downloaded to the FPGA chip. Okay, but if you just want to do simulation, you should pick that simulation file as the output. Okay. Okay, if you select any one of these things, now you can do the synthesis by going to the process menu and select run all, rerun all. Okay, so this select this export files using a VHDL simulation and do the run all, and the synthesis tools will go and work on all the 5 files, and then it runs through many different steps. Okay, it does the first do the synthesis and do the mapping, place and route, and it would do some analysis and give you some information about how much delay, the maximum delay the circuit would require to get one end to the other. So it will do all these things automatically, and I really don't have much clue about what it is actually doing, but it's try to look at your VHDL design and try to assign proper logic to the FPGA cells inside the chip, and make the proper connections among all the logic components, and eventually it will decide where to put the logic and how to get the whole thing connected. So all these things, I don't care. Okay, that's probably you know, in the actual chip manufacturer, and they will have teams of engineers to do the logic design and placement, and eventually, you know, in the old days, they will actually plot out all the circuits and use a ruby leaf, the red plastic sheet, cut out the circuit, and then do the masks. Okay, so I think it's saying complete successfully, and I think usually it tells the truth. So once we have the simulation done, we can go to the go to the simulator. So in tools, and go down here, it's the simulation wizard. Okay. All right. It wants you to give the simulation project a name. So giving it the same name, usually it's safe. And it asks you want to RTL or the other post map gate level and the post route gate level plus timing. So these are different levels of simulation. Usually the first level is sufficient, because if anything is wrong, that you can see that in the RTL simulation. Okay, so I think the simulator is being called. Okay, the simulator is actually provided by another company, Active HDL. So in the lattice, it has much reduced version, particularly for this for the Bravia 2 chip. It's much reduced. The capability is much reduced, but it's sufficient for our purposes. Okay, and you can see that it produces the waveforms that a few microseconds, I mean nanosecond of activity. So here in the these are the available signals. You know, much of the signal information are redundant, so you really don't need all these all the signals. You want to pick the signals that you really want to see. Okay, so here and this panel allows you to pick different signals and then put them onto this this display when you actually running the simulator. Okay, here. So here, I think generally this is very interesting in that you know, the top one is A clock. Okay, And that's a 50 megahertz. And 50 megahertz is too fast. So I cut the clock speed, reduce the speed by 2. So the B clock is the clock that I want to run the CPU with. So you can see the B clock is actually, the period is twice as the A clock. And then you can see the next line is the address. You have address 0, 1, 2, 3, 4, 5, and then it has one FFE. So this is the correct correct sequence. Then you can read the data input. The data input, you get 21, 0, and 1F, 22 FE. That's at 1F, 80, 1F. That's at, well, I forgot what the. And this is actually the data coming out of the memory. So these are the very useful information that you can see. Things are clocking. The clocking is correct, and it's reading the data from the memory correctly. And then, but for the details of this process, much of the information are all duplicated. Okay, so you really don't have too many things that too many interesting things in this display. Okay, there you see you have all these signals are in the top level design. Okay, in the top level design you have all these signals, and which automatically the simulator automatically display all these signals. Okay, and but these signals much of the signals are redundant, so you really don't give you too much information.
It's not running a practical program, is it?
Yes, yes, it is running the E4 system. Okay, and the actually it's running a first few instructions.
So that's why you knew that it was supposed to jump to that particular address at that
Yes,
point. Okay.
yes, yes, and it's showing. It's not yet jumping to the code. It is initializing the return stack and the data stack.
How much that bar at the bottom? So you're displaying half of what it gave you on the simulator.
Oh no! This is it's running 1 microsecond. Is that right? Yes. So it defaults in running give you 1 microsecond of the data. Okay, and then I'll show you how to run more. Okay, but the first thing I want to show you is the what's the really important signals that I want to see. Okay, so here I don't really need to see the A clock. B clock is the clock that I will be running. So I can delete this one. A. Okay. Let me see. I think I'm in trouble with it. What to do? Okay. Jen, I think cockpit error. I don't know why it is giving me that big blue thing. But what I want to show you is here. You know, in here, I really want to see some signals inside the CPU module, not on the top. Okay, so to to go into the CPU itself, you can, it's here, I have the CPU module. And if I click on it, there, now the signal lists all the signal in this CPU module. And in this CPU module, what I'm interested, what I'm most interested is this R stack. This R stack is actually the data stack in the system. So I want to see what happens on the data stack. So if I don't know if I can do this now. No, it doesn't want me to do that. I don't quite understand why I cannot delete this signal, because I used to be able to delete most of the signals. I don't care. And generally, if I left click, I'm not trying to zoom in or zoom out. What I want is to delete it. Okay, delete. All right, good. Okay, so I delete a lot of well, I'm sorry. The let's don't worry about it. But you can delete all the signals, and you can pick the signals that you really wanted to see. I hope. No, it's not. There's some problems here, which I cannot explain. Oh, okay, there you are. So I'm having the having the data stack there. That's good. Let me just do this one thing. I'll put it on the top. Okay. Oh, no, not this way. So I have the data stack, 32 levels of it, so I can see all of them. But I really don't want to see all of them. Okay. I just want to put it on the top. Okay. So this is the data stack. We'll try to see. All right. So what I want to do, I have put this data stack there, and now to run it for 10 minutes, in 10 milliseconds. Why 10 milliseconds? 10 milliseconds, I can see all the I/O. I can see the ASCII code coming out of the serial port. Okay. So here, I would simulation. I would restart simulation. I hope it restarts okay. All right. And okay, I want to run until this is only allow me to run 100 nanosecond. That's not enough to see much. So I would say 10 millisecond. Okay. All right. Okay. Hope it's running. So it will run, collect all the waveforms for 10 milliseconds.
10 real milliseconds?
Yeah, for 10 milliseconds, I hope. Hey, run. Yeah, I hope it's running. Yeah, it will take a while to run at 10 milliseconds because yeah, because it is 25 megahertz. Yeah, okay. It has all the form, and then you can see that everything's still running quite all right. Okay, you can see the addresses are not going anywhere strange. But if you when you first implemented, usually the address stuck at one point, and that's when you have problem. So it's running to the 10 millisecond down there. What I want to show you is the serial port. Okay, here, this is the UART output and UART input. There's nothing input here. I cannot input anything there. But the output, what I want to show you is this output. Now, this is up to 1 millisecond. It shows only a few clocks up to 10 milliseconds. So what I want to do is to reduce the scale here. I want to reduce the time scale until I can see something. Okay, see here? That's the output of the UART. Okay, so and this is really what when you see that UART output. When I saw that, okay, the CPU is okay. The CPU is right. Okay, and here you can it says if you can read the UART code, I think many of them can. This is the let me see. This is the carriage return, line feed, and then the EP 8080 and so forth. That's a sign out message. Okay, so that's what you need to do. If you see this screen, if you implement eForce and see this screen, CPU is right, is correct. The eForce may still have problems, but I think this is the most difficult, the highest peak that you have to climb. Any comment? Any? Okay, let me just go on to the next step. This is the simulator. Okay, and you can close it off. I don't mind it. Well, I didn't show you the stack, the data stack, but we don't have that much time. So here, I want to show you the next step. Next step is to pick this out file, the JEDEC file. And this is the actual image that should be downloaded into the FPGA. Initialize all the circuitry and all the RAM memory that you want to. So it's if you have this file, it can be burned into the FPGA chip, and then the FPGA chip, when it starts, it would run the code that's in the RAM memory. So let's pick this one and run the synthesize again. Pick this one, do the synthesis. No, this is the process. So run all. So it's doing. I think I don't have to do everything there. I think I can just pick this one and hit rerun. And probably everything else, if there's any, if you didn't change any code, it will not run the code that it has already run. But the safe thing is to just let it run everything. Okay, it will take a couple minutes until it finishes. So, yes.
on in order for an FPGA to simulate what a CPU is doing, does it have to essentially run through everything in sequence, or does it run? Does it count up and down? I thought FPGA had particular rules about how its elements can be accessed.
Oh, the details of how this FPGA actually run, I don't understand. Okay, how I don't.
You have one on your little board there, right?
Yes, yes.
It's how do you make it actually run? You just
okay.
add power?
No, it's the yes. Just add power, and with the right code. Right, the image.
The problem is the FPGA manufacturers don't tell
Yeah.
you what they're actually. They'll tell you about the individual elements.
Yes, yes, exactly, exactly. Yeah, if you read the documentation on FPGA, it will tell you how each element, what's the logic inside each element, and then it will talk about the connections. You know, there are many levels of connections among the cells, and but these things, if you want to worry about them, you can, but there's no tool. They do not provide tools for you to look at each individual cell and actually specify how each cell should behave and how things are connected. So I think if you wanted to do,
just within a window of the spec of how the chip was made.
yes, yes, and I think in the earlier days, they even provide ways the image file, the format of the image file, so you can actually look at the bits that goes into the chip, which defines the function of all the components. But that's really what we are interested in. What we now they provide the VHDL technology or Verilog technology. So all you have to do is to specify your logic in VHDL or in in Verilog, and then the synthesis tool will take care of all these assignments. And most of the time, it try to optimize. Okay, yeah. In the synthesis, there's lots of choices that you can make. You can order it to synthesize, optimize the area, or optimize the speed. Okay, these are strategies that you can pick, and it allows you to pick. If your speed is what you're concerned, you can pick the speed, optimize for speed, so it will run the fastest. But it would probably use more logic to achieve higher speed. But if you are concerned, your concern is manage area. You have a big chip. You want it to fit in certain area, and you can specify, I want to optimize the area, and it probably will implement so that it will run slower, but it will save memory for you.
Now, if I were designing a chip to be directly burned onto a piece of silicon,
yes,
I could make the chip a certain size.
Mm-hmm.
If I designed it to be simulated by the FPGA, it would require a lot more area of active transistors, right?
Mm-hmm.
Is there a figure for that, or is this like, if this is 1-to-1, would it take 100-to-1 or 1,000-to-1 to simulate that chip in an FPGA, or is there any metric on that?
Oh yeah, oh yeah. I think the design, you see here, it says reports, the design summary. Okay, it has all these reports.
So your scaling would go up and down as you check.
Yes. Yeah, if you depend upon the options or the strategy you have to take.
You could do. I mean,
yeah.
Make it almost be correct, but would make a lot of mistakes in your test?
It's so here. The point is that to design a chip, you lay out the assign logic to transistors.
Yeah.
And make physical connections among the transistors, like Chuck is doing with his chip.
Yeah, that's
very difficult. It's a very difficult. It's very difficult and very easy to make mistakes. So the beauty of this FPGA kit is that it has already built in so much logic, so much memory on the chip, and you can use high-level language to specify what you really wanted. Okay, and so you are basically use this kit. You are thinking in the VHDL level. You are thinking about registers. You are thinking about how the information from one register goes to the another. How the ALU, how you would want to implement add or subtract, add with carry. Okay, all these things can be specified in VHDL. Okay, and you don't have to worry about the carry chain. That's one of the very important thing, very extremely important thing in doing a chip design.
Okay.
How the carry propagates. But the VHDL right now, it takes care of that. Okay, if you say I wanted this chip to run fast, okay, it will optimize this carry propagation so that it will run the fastest. Probably it will add more logic to it, so it can run.
Something would have to get subtracted. Something would take that ability away from some other capability you wanted to have.
The nice thing about it is you don't have to worry about that. Okay, you have to worry about logic. Okay, and then the tools would take your logic and translate it into physical chip that actually runs. Okay, and I think looking at Chuck, what he's doing, nobody could understand him. Nobody could, if he leaves, nobody can change anything. Okay, so that's what and that's why I split with him, because he has his thinking.
Propagate his methodology to other people, could he?
No, he couldn't. He couldn't. Yeah.
Try to do it.
Yeah. Yeah.
IntelliSys and spent millions of dollars.
But I think you see
created with traditional technologies.
Yeah.
Outside of OCAD.
Yeah.
Oh, but within OCAD.
Within OCAD, Chuck is able to do it.
Yeah.
But OCAD is Chuck.
Yes.
Yeah.
Yes. Okay. So here, the EP16, EP32, this design are basically Chuck's design. Okay, and Chuck used that design in the green array. Okay, and he had add many things around it, especially the I/O. I mean the input output and the communication, and execute in the I/O port. And these are very interesting. But the core of it, the EP16, if we expand it to EP18, it's the same as Chuck's green chip cores. So if you do care, you can actually use this design in VHDL and rewrite the green array. Yeah, you have a question?
Is it possible to do asynchronous logic on a FPGA like this? Because I know the GA144 has these async.
Yes, yes. That's one of the very clever thing that Chuck did. And this is the I don't know how to do it here. Okay.
We were doing the V8 at IntelliSys before we had chips. We got many nodes inside of a FPGA, but it is still synchronous.
Yeah. Yeah.
Doing the asynchronous logic is not possible with the clock structure that is in an FPGA. You have to remove the clock.
So I have counter data for that. The RISC-V community does have an asynchronous RISC-V that is synthesizable in a Xilinx FPGA.
I see.
It is, you have to use certain types of gates with which Chuck Moore does not use. From what I understand, and please understand that my understanding of Chuck's design is very limited. Chuck's design is actually at the core synchronous, but he clocks it with a ring oscillator that is sitting inside the core itself. That is to say, he's not accepting outside clocks. What the RISC-V community does with the FPGA is they use synchronizing logic gates. That is to say, this gate doesn't become true until all inputs become true. And then likewise, it doesn't become false again until all inputs go false. So in that way, you maintain locksets between the two asynchronous things. So your logic density suffers because it's not really designed to support that style of logic. But it is doable if you're willing to sacrifice the gate.
Okay, I think let's get back to this thing because the synthesis is done.
One thing I have lost in the setup is you've got your zip file that you're telling people where
Yes.
on Dropbox.
Yeah.
Can you walk through taking that and getting it into Lattice Diamond?
Okay. Yeah. Let's.
There's a step that I can't remember how I did it.
Yes. Okay. Yeah. Let me just finish this one. There's only one step away from the end. So I have resynthesized it, and I get I got an image. I hope that I can download to the. Okay, so this XCF file is the programming file, and this is the one that would program the chip. Okay, so we have that, and we just go to the tool and go to the programmer. Okay, load the programmer. The programmer is running through the USB cable, and there you pick everything seems to be okay. We pick this one, and it says flash erase program and verify. So we want to burn the chip. Okay, and there's a whole bunch of buttons there, and this button is the program button. Okay, selected window firewall block feature. Allow. Hey.
Nope.
Okay. Okay, so I have this. It's burned successfully. Okay, and now let me take a look at the hyperterminal. Yes, you see hyperterminal sign up. So there, it is executing. And do. And if I say words, got the words, you want to say colon test CR quote hello world and the test. It says hello world, okay. And if I do FF04 C store, so I want to turn off all these 4 LEDs, so they turn off. I want to turn on one of it, FF04 C store. I just want to turn on one, and there's one. Okay, so this is well, I want everybody to go. Okay, if you can do that, do the hello. If you do turn on one of the LED, turn it off, you are done. Okay, now back to you. What I'm providing everybody is yeah, it's about the lunchtime. Okay, let me just show you the package that I'm distributing, and where is it? You see the memory is okay there. Okay, so I'm sending people this zip file, and this zip file contains the VHDL file, the 5 VHDL file, and also the LPF file. So these you need to move into the your Diamond IDE project. Okay, and then the I have synthesized the EP202 memory. That's a memory file that's included in the RAM memory VHDL. So it's already there. You don't have to worry about it. And the point is that if you want to write your own E4 system, then you have to follow this build 202 batch. And that build 202 batch file would assemble the AD eForce 202 or 203 assembly, and then produce the ADEF202.exe file. And all the code, all the eForce code is in the .exe file, but it is displayed by 200 hex bytes from the origin. So what you need to do is to take the code from 200H up to where the limit, and then produce EP202.mem file, which is a text file that the IDE tool will take. And to generate the memory, VHDL file. So that's a procedure. You need to have have something that you can assemble. You can produce a binary file, and you have to modify that file in the form that IDE can use. That's a .men file. Yeah, that's they are all provided.
What I'm missing right now is when I open up Diamond and I've got the zip file. Now do I open a project, or
Yes.
if I try to open a project, it's now looking for an LDF file, not an LPF. Where do I get the LDF?
Oh, LDF is the project file.
So I just create a new project file?
If you create a new project, then it will produce the LDF file automatically.
Okay.
Okay, that's a project file. Okay.
So then I just do EP80 and put it into that where I created the zip. EP80, select that folder. Then next, add source, all of the VHDLs that are there. Open. Next. Then I've got to tell it what device I have.
Yeah. It's just it's the
Which one is it? The Lattice XP2.
Yeah. So yeah, you just basically follow the procedures in the IDE, and it tells you how to open a project, how to select or set up this project for targeted for the particular chip on the
XP2.
Yes, XP2 and I think XP2 and something C. Okay, the particular chip number. You have to select that. Okay. All right. Let's don't worry about this thing. We'll talk about it later. I don't have any time now. I just want to clock through all the slides and show you what I intended to do. Okay, the CPU architecture. I want to review these things, but we don't have time. Maybe in the afternoon, you can give me some time to go through it better. The cardiac, von Neumann, IBM 701, IBM 360, PDP-1, PDP-8, PDP-11, Nova, Spark, MIPS, ARMS. And these things, I want to show you the instruction set. But we don't have time. Let's go lunch first. And if you have time, I can show you the details. Thank you very much. Bye-bye. Until lunch, until after lunch.
So this is Amazon's?
Yes,
pad?
the file.
It's called what?
File.
File?
Yeah.
F-I-L-E?
F-I-L-E.
Amazon File. Because
$50.
someone gave me an Amazon gift card.
Oh, okay, yeah.
Ooh, it's
okay.
epic. Can you? Is it openable? I mean, like, can you actually put a programming language on it, or
that's what I'm thinking. Yeah. So I need a handle to write an API.
I see.
Okay, it has everything that the force need. Okay, you have input, output.
Okay.
It has keyboard input.
That's the keyboards and all that.
And the display and
you have the info about that. You don't have the. I mean,
no.
They don't release anything.
No.
Yeah. I used to have these. They used to have these sharp pocket computers. That have one line keyboard.
Yes.
Never released any of the code. And some guy in Southern California hacked it with stuff.
Yeah, right.
So we actually found a way to get out of it, and we were making LCDs work with these things. It was a thrilling thing, but I did need help with that. Pretty hard.
Okay, let's go lunch.
Yeah. Well, I have to run.
Oh, you have to go?
I need to. Look at this rack mount has handles. I need 2 handles. Is there a junk box in Stanford? Otherwise, I have to go down to Santa Clara. And,
I think you can go to the high tech or this surplus
where is
store.
that?
I think there are 2. One at the
Halted. That's where I'm going to go.
Okay.
I know. They just moved.
No, I think it's yes.
Move that way. Move that way. Let me tell you.